Hi, welcome to another video. I'm going to look at the chapter 6 of this special publication of economic geology. The title is Transcrustal Magmatic Controls on the Size of Porphyry Copper Systems, State of Knowledge and Open Questions. Here is a summary of the methods used and innovative aspects of this article. First of all, we have volatile solubility modeling, during which they modeled how water, sulfur, chlorine, and copper behave during magma evolution and exsolution. Then we have sulfide saturation and partitioning calculations. They've used SCSS or sulfur concentration and sulfide saturation and copper sulfur's partitioning models to track metal loss or retention. Then we have magma flux rate modeling, which quantified the volumetric rate of magma injected and linked it to thermal sustainability of melt bodies in the crust. The next method used is thermal evolution modeling of magma chambers. They assessed conditions required to keep melt partially molten long enough to accumulate and release ore forming fluids. Then we have degassing pathway simulations. They investigated bubble formation, channel flow, and fluid release under different crystallinity and volatile saturation rates and states. Then we have redox buffer comparisons. They explored the impact of oxidation state on sulfur and copper behavior during magmatic evolution. We have salinity and copper mobility and solubility modeling, during which they analyze how chlorine content and redox state affect copper solubility and transport in a magmatic fluid. And finally, we have integration with natural systems, during which they validated models using examples from known porphyry systems like El Teniente and Colung. So what are the innovative aspects of this article? First of all, we have transcrustal system integration. They combined lower crust melt integration with upper crust degassing, and they linked deep and shallow processes with each other. The second thing is critical magma flux threshold concept. The authors here define the processing window where sufficient volume and rate sustain ore forming systems and linking intrusion dynamics to deposit size. The next is MSS resorption insight. They identified metal remobilization from previously recrystallized magmatic sulfides as a key enrichment step during late stage evolution. The next innovative aspect is redox chlorine integration interaction modeling. They demonstrated that slightly reduced conditions with high chlorine maximize copper solubility in fluids and shifting exploration focus. The next thing is delayed degassing mechanism. Authors highlighted how water undersaturated magmas allow for enhanced copper delivery during delayed and focused degassing events. And finally, they provided quantitative fertility predictors. They developed a multi-parameter framework including fugacity of oxygen, water content, chlorine, and volume for forecasting copper deposit potential before eruption. If you ever wonder why some copper mines hold just a bit of metal while others pump out enough copper to wire entire continents, this article is trying to answer that question. These are porphyry copper giants, but geologically speaking, they all started the same way with magma. So, why they're different in size and metal content? These deposits can range from about 0.01 million tons of copper or copper content to more than 100 million tons. And that's a large range, over 5 orders of magnitude. So we have same processes and vastly different results. Why? Let's look deeper into what's called a transcrustal magmatic system. On the left image, porphyry forming magmas start their life in the lower crust. Their basaltic magmas rises, differentiates, and turns into more felsic, metal-rich magma. This differentiated melt then migrates upward, carrying copper, sulfur, chlorine, and water. So the size of porphyry copper deposits, or porphyry deposit in general, largely depends on what happens during these 3 stages. First of all, we have magma differentiation in the lower crust, which is drawn in black. And then we have ascent and storage in upper crustal chambers. And finally, we have degassing of metal-rich fluids. So when we talk about global copper supply, these deposits are giants, but how do their tonnage and grade related to each other? In panel A, on the right side, we see a strong positive correlation between copper tonnage and ore tonnage. That means that the more total of ore you have, the more copper you tend to get. And it's no surprise, size matters in bulk mining. But when you look at the panel B, it gets interesting. As copper tonnage increases, grade doesn't, in fact, higher tonnage deposits often come with lower grades. And it's an inverse trend. You have large tonnage and lower grade, which is actually typical of porphyry systems. They're vast, they're huge, but not rich in concentration. So, what are the curves around the edges? They show the probability density. Most deposits cluster in the lower tonnage and mid-grade range, but a few outliers dominate the global copper supply. So when we are exploring for porphyry copper, it's not just about chasing high grade, it's about understanding the balance between the scale and quality. Okay. These charts might look like complex, but there is a simple and powerful story here. We have panel A, which is sulfur solubility versus magma evolution. As magma evolves, meaning it cools and becomes more silica rich, it hits a chemical threshold called sulfide saturation. That's the point where sulfur can no longer stay dissolved in the melt. Instead, it starts forming solid sulfide minerals. And that's critical because sulfide minerals love copper, they're chalcophile. The curve here shows the sulfide concentration at sulfide saturation, which is SCSS for short. So as silica increases, the magma holds less and less sulfur. So when it saturates early at low silica, it locks up more copper deep in the crust. That means by the time the magma gets near the surface, a lot of copper is already gone. They're trapped in solid sulfides far below. Then we have panel B. At panel B we have sulfur content start at 2000 ppm, and that's high. This magma's heat saturation early, and as a result, copper concentration drops sharply as the magma evolves. And you can see that copper-copper initial ratio fall off fast. The melt becomes copper depleted long before it ever has the chance to form a porphyry system. Then we have panel C, which starts at 1000 ppm copper content. This time, sulfide saturation happens later, which allows the magma to retain much more of its copper content during its journey. So when it finally reaches the upper crust and starts degassing, it's still copper rich and ready to build a world-class porphyry deposit. This figure tells us something big. The chemistry of deep crust sets the stage for surface ore. If sulfur is too high too early, copper gets locked away too deep. But if the magma has just the right sulfur budget and evolves carefully, it preserves copper until it really matters, when it can exsolve into hydrothermal fluids and start building ore. So next time you think about porphyry systems, remember that the battle for copper is often won or lost, but deep underground. Here in panel A, we have wet magma with 5.6% water content. Here we are looking at key turning points in magma degassing and copper mobilization. So what happens when magma starts to cool and degas in panel A with 5.6% copper? Well, in this graph we see the behavior of a wet magma reaching water with at temperatures drop from 950 to 700, and then the degassing process kicks in. At higher temperatures, gas bubbles begin to form, but they're trapped in the melt. They're suspended like fizz in a soda bottle. Then comes a tipping point as the magma becomes more crystalline. These bubbles find pathways to escape. That's the channel flow outgassing phase. And it's critical because that's when volatiles like sulfur and copper start moving. Now focus on the red and dashed curves. These show sulfur solubility under different oxidation states. At higher oxidation fugacity, which is solid line, NNO plus 1.5, which sulfur prefers to stay in the melt or form sulfate minerals, so less sulfur goes into the fluid. But under more reduced conditions, which is the dashed line NNO 0.5, sulfur is more fluid mobile. That means more copper can hitch a ride, because sulfur and copper travel together in magmatic fluids. So if you're building a porphyry system, a moderately reduced condition is actually favorable because they liberate copper earlier and more efficiently. Then we have panel B. So let's shift to a drier scenario in this panel with only 3.5% water. This changes everything because it starts out water under saturation. The magma doesn't degas immediately, so no bubbling, no copper escape yet, but as it cools, it enters a special stage called MSS resorption, which stands for magmatic sulfide resorption. And it's a process where previously formed sulfides dissolve back into the melt and release their stored copper and sulfur. It's like magma takes a second breath, a late stage recharge that gives the fluid another shot at collecting ore metals. Now look at the blue curve, copper in fluid. It rises sharply as we hit the outgassing window again. This delayed but enriched fluid phase is perfect for porphyry formation, with lots of copper ready to move toward the upper crust. So here's the takeaway. Wet magmas degas early and continuously, but may lose some copper unless conditions are just right. Drier magmas delay degassing, but thanks to MSS resorption process, they can supercharge copper mobility later in the game. And in both cases, the oxygen fugacity, water content, and timing of outgassing all determine whether you're building a giant ore deposit or missing the window. The chemistry of copper delivery is not just about where magma goes, it's about when and how it breathes. Here's a conclusion then of this stage, this part of the article. First of all, magmas need the right amount of water. Not too early, not too wet either. A little water helps form bubbles that carry metals, but too much water can cause early degassing and copper loss. The second thing is timing is everything. A bit of delay before the magma starts to degas gives it a chance to build up copper. That way, when it does release fluid, it's rich enough to form an ore deposit. And the third thing is that oxygen levels matter. Slightly reducing conditions, meaning just below oxidizing, helps sulfur and copper move into the fluid phase instead of getting trapped in minerals too early. So in short, the best porphyry copper systems come from magmas that cook slowly, don't degas too early, and contain just the right mix of water, sulfur, and oxidation state. Here in these diagrams, we have salinity and NNO values. NNO stands for nickel-nickel oxide buffer, which is a standard benchmark for measuring oxygen fugacity or how oxidized the magma is. In these graphs, we are comparing two oxidation states, NNO plus 105, which is oxidized condition, and NNO 0.05, which is a reduced condition. Let's start with salinity and how salty the magmatic fluid becomes as the system cools. Each curve shows a different starting chlorine content in the melt from 1000 to 3000 ppm. At high oxygen conditions, plus 105 NNO, salinity increases steadily with cooling. It means more chlorine in the melt means more salt in the fluid. It's quite simple and efficient. But when the magma is more reduced and at 0.05 NNO values, the story changes. Even with the same chlorine starting point, salinity builds more slowly and plateaus earlier. So it means less oxygen means less efficient salt delivery. In panel D, we have copper under oxidized conditions, NNO plus 105, at which copper rises early with temperature and chlorine, but then tapers off as the system cools. It starts strong but fizzles. Then look at under slightly reduced conditions, NNO 0.5. Copper curves spike higher and stay elevated longer. Why? Because reduced fluids are better at transporting copper, especially in the presence of chlorine. You can think of it like this. Chlorine is a carrier. An oxidation state determines how much copper it can carry. When we have reduced plus chlorine-rich fluid, it's perfect combo for copper-rich fluids. So what's the takeaway? If your magma starts with enough chlorine and just the right oxygen balance, not too oxidized, not too reduced, you generate fluids that are salty and copper-rich and are capable of transporting metals efficiently into the crust. And that's how giant porphyry copper deposits get started, not just from the heat and pressure, but from a precise chemistry and timing. So, how fast you inject magma might decide if you strike copper. Let's talk about timing here. How much magma do you need and how fast do you have to pump it into the crust to actually make a porphyry copper deposit? In this graph, the x-axis horizontal shows the volumetric intrusion rate. It's basically how quickly magma is injected into the crust in cubic kilometers per year. And we have y-axis, which shows the total volume of magma that accumulates over time. So we are looking at both how fast and how much magma builds up in a given system. Over on the far left, you can see that if magma is intruded too slowly, even over millions of years, you're likely just forming a barren pluton, a granite body with no copper potential. The magma cools between pulses and no sustained hydrothermal system gets going. But in the middle, that's the sweet spot. Inject magma fast enough, but not explosively, and you maintain a partially molten magma chamber. That's where porphyry deposits like El Teniente, Kulung, and Bajo de la Lumbrera formed. These giants were born in this stable zone of moderate intrusion rates and sustained heat, enough to mobilize fluids, but not trigger immediate eruptions. Now check out the shaded zone labeled A. This marks the minimum thermal and volume conditions needed to keep magma partially molten long enough for sulfur-rich copper-laden fluids to accumulate and migrate. Below this zone we have magma pulses, which freeze too quickly. That means no melt, no fluids, and no copper. Above it, we are in the right zone for fluid saturation, focused degassing, and eventually ore deposition. Think of this field as your entry ticket into porphyry forming territory. So if you're exploring for porphyry copper, it's not enough to see signs of past magmatism. You want evidence of large, long-lived, and well-fed magmatic system that cooked slowly over time, stayed molten enough to outgas, and didn't erupt too early. Because if your magma system never crossed into that critical wedge, you're probably just looking at a granite batholith, not a copper giant. On this chart, we've got magma volume on the y-axis and maximum copper mass on the x-axis. They're both on a large scale because log scale because we are dealing with huge ranges and values. The big gray diagonal zone, what's that? That's the copper potential zone. It shows the range of extractable copper depending on how much copper and chlorine were in the magma to begin with. If you have high copper and high chlorine, we are on the lower right edge, and with low copper and low and chlorine, we are at upper left range. Now let's talk about a real-world example which has been mentioned in this article, and it's Yerington deposit in Nevada. There's a whole batholith down there, tons of rock, but only a slice of it actually contributed to forming a copper deposit. The dot for whole Yerington batholith shows the total magma volume, but the dot for the lower Pluton down there, that's the effective Pluton. It's a part that was hot and fluid rich and focused enough to actually form a ore and deposit. So this vertical line between them, that's a reality check. Not all magma matters. Only a fraction of the batholith contributes to the final deposit. So if you want a giant porphyry deposit based on this diagram, you either need a ton of magma with average chemistry or a smaller magma body that is extra rich in copper and chlorine. Here's the final slide and conclusion. What really builds a copper giant? It's not just a magma. It's a magma. It's an entire magmatic system. You need more than metal-rich melt. You need enough magma injected at just the right place, and you need fluid-rich melts that stick around without erupting too soon. You need delayed degassing so copper can concentrate, and a carefully balanced combination of water, chlorine, and oxidation state. Because even fertile magmas can fail if the plumbing is not right. So when we are exploring, we are not just chasing high copper values. We are looking for evidence of a long-lived, well-fed, and slowly degassing magmatic system, with melt pockets that stay hot, build pressure, and slowly release metal-rich fluids into the upper crust. Big deposits don't come from explosive bursts. They come from stable, simmering magma systems, the kind that stay active for hundreds of thousands of years. That's what really builds a copper giant. Thanks for watching.